University of Michigan. I suspect many of you are already familiar with his wonderful 2010 book, A Vast Machine, but if you're not, I strongly encourage you to check it out because it's a great book. So, take it away.
Thanks. I'm not going to talk about carbon pricing. I just like this cartoon, but if you didn't notice it, this is the really good part. We better hurry. No, that's the great thing about this challenge. So, I'm not going to talk very much about this phenomenon, but this is the kind of phenomenon that I want to talk about today. The fact that climate science today is an extremely public science. So what we're going to do, I'll talk about what knowledge infrastructures are, what I mean by that, and we'll do a little history of weather forecasting and climate science, and then talk about reproducibility and where climate knowledge is going. So what's a knowledge infrastructure? Well, we're in a conference with a lot of philosophers, and philosophers tend to think about things in terms of truth, epistemology, logic, things like that. I come out of a different tradition that's related, which is the science and technology studies tradition, and we tend to look at it more as a socio-technical phenomenon, scientific knowledge. So to say that you claim that something is knowledge needs to be a claim about having an infrastructure that supports that knowledge. So a knowledge infrastructure is a network of people and instruments, other kinds of equipment and institutions that support knowledge. That's what underlies it. In the sense of scientific knowledge, I'm usually thinking about things that are routine and widely accepted, things that we use all the time. And examples of those from outside climate science are things like national census bureaus, the Bureau of Labor Statistics, the Centers for Disease Control. But then, of course, we have weather forecasting and the IPCC and other institutional structures that support this knowledge. All right, so in the talk, that's what I'm talking about, and what I want to take you back to for a minute is the distant world of 20 years ago, when something like the following things were true of most science. It was built as a set of pyramids of expertise. There were people and institutions that were at the very top, and they were the most authoritative, and then others that were less so. The reputation systems were based on who you worked with, what institution you went to, you were record in peer review, and you were past performance overall. In this distant universe, your data and your models belonged to you. And that was your work product, and for the most part, people did not publish either data or models. They published instead the synthesis of those things, so you would get a graph representing some data, but you would not get a publication that contained the raw data that went into that product. Code was the same way. I mean, it was often shared, but not formally, not in the sense of being published. It might be borrowed from someone you knew. Also in this world, a lot of data and a lot of code were produced by people who were not considered scientists. They were technicians, they were programmers. They might be quite good at what they did, but they were not actually part of that world. That was, since that they had done that, they were never, since they were not in this kind of official line, they were not credited. Quality control in this world was done by peer review, and that is, I don't think I need to explain that to this audience. In peer review, data and code could be reviewed, but they almost never were. So you didn't have that access, and you didn't demand it unless you had a really deep question or it was very interesting and you wanted to take the time to try to obtain those things, which is very hard. That's all changing. In fact, it has changed. We're done with the change for the most part, and that's what I want to talk about today. If you haven't seen this book by David Weinberger, it's really fun and entertaining. He's a kind of a very, very intelligent journalist who has become sort of a library science guru. And we'll talk about all these things as we go on, but the the point is that the publication of everything has made science much more public than it once was. Publication, publish, public, those things are all obviously connected. And that's creating a kind of different world of what knowledge is and who counts as a reviewer. Okay, so a little bit of history. I'm essentially a historian. It's not the only thing I do, but I'm not going to spend as much time as I'd like to on this. It's a very long story. Jim gave you some of it yesterday. I just want to hit a few highlights. By the middle of the 19th century, especially in the last quarter of the 19th century, weather forecasting looked a lot like it does today, in the sense that when you saw a weather map, you can see here there's a high pressure zone, there are ocean currents, there are isolines. The kind of basic structure of how things looked and were done had evolved to something like its present form. From the end of the 19th century into the 1960s, we got truly global coverage by surface stations. That was not true in 1870 when it was mostly Europe and North America, but by 1960, the land masses of the world were pretty well covered by surface stations. You can see that the oceans, there are places where there are not many islands, especially in the South Pacific, and these areas are poorly covered, and that's less true today, but it's still an issue. And starting in the 1950s, we got computer models for weather forecasting, which didn't look like this in the 1950s, but they pretty soon took this shape where you have a grid in which observations are sucked in, data are interpolated to grid points, and then moved forward in time with physical equations that simulate the behavior of the atmosphere. In the 60s, they started developing this thing, the World Weather Watch, which actually has a much longer history. There was a sort of quasi-global network even at the end of the 19th century. And by the time you got shortwave radio, observations were being broadcast all over the world in a kind of kludgy way. But this was a much more systematic and concerted attempt to systematize the whole process. So you have a global observing system consisting of stations, satellites, ships, buoys, many other platforms that bring back observations. Those are communicated by a global telecommunication system developed before the internet and facing a lot of the same problems. Its history is quite interesting in that respect, because you see them wrestling with the same issues that the people who developed the internet did later. Data go to global forecasting centers where they're processed into global data of various sorts and global forecasts. And those are then sent back out to national centers, which do further processing and make national and local forecasts from some of those data. So with computer modeling, you begin to get a really steady and visible improvement in forecast skill. Now, Jim talked about this yesterday. That what this graph is about is the forecast at the 500 millibar level. So we're talking about jet airplanes, not that altitude, not the surface where we live. So this is not indicative of the quality of surface forecasting, but it's still important because that level steers weather down below. And you can see these are various computers coming in, and with them, the models the grid scales get finer, and the resolution is higher, and more processes are incorporated, and there's a very steady kind of improvement. So, the place I'm going with this is that weather forecasting is really what we are talking about when we say knowledge infrastructures. So people rely on it. You check it to see if you're going to need an umbrella, to figure out what you're going to wear, things like that. And you know it isn't perfect. You know it might be wrong, but you still rely on it because it's right more than it's wrong. And that's a lot of our knowledge is like that. So this is not unique. I mean, even census figures are really, in a lot of ways, simulations of populations rather than direct counts. Okay, little history of climate science. I'll slow down a little bit. So Jim talked yesterday about the calendar effect. Guy Stuart Callender, this is his first article about the carbon dioxide effect in 1938. This is a very interesting article to read, partly because the discussion that took place at the Royal Meteorological Society is published along with it, so you could read what people said about this paper when it was being produced. So Callender analyzed, it took about 150 stations and analyzed the temperature of the globe using those stations. He was a very careful scientist. He took a great care to pick stations that had continuous and pretty reliable records to do this. And what he saw was a 0.4 degrees C rise in global temperature across this period. And then he tried to separate out from that what part of that might be caused by carbon dioxide increase. So he's showing a rising temperature, and he's showing a carbon dioxide effect that doesn't account for the whole rise, but accounts for part of it. So that was the claim. Now, what did his colleagues say at the Royal Meteorological Society? So these three guys, Simpson, Brooks, and Brunt, were some of the foremost meteorologists of their day. So they were the world experts on this kind of thing. And all of them said basically, well, he might be right, but there's no way we can know. First of all, it might be a coincidence. Climate changes all the time. We don't really understand why. Secondly, maybe these temperature increases you're seeing at the surface are explained by changes in the general circulation, so the global motions of air, which are vertical as well as horizontal. And that they did not know much about at that time. And then Brunt also, if there's a change in heat absorption caused by carbon dioxide, that would cause complicated effects on the general circulation, not just a simple linear temperature increase. So they're basically all saying it's a lot more complicated and we don't know enough about the global circulation to tell if you're right. So Jim showed this yesterday. This is Farrell in 1860. Diagram of the winds, the major circulatory cells, the Hadley cell, the Farrell cell, the polar cell, they're all here, and a modern diagram from just a few years ago looks very, very similar. Right, so the basic understanding of the large-scale circulation was there, but the details were what mattered, and that's what they didn't understand and couldn't understand with the tools they had at that time. So this is before regular radiosonde measurements. There was some measurement at altitude, but not very high relative to the total height of the atmosphere. And it was spotty and not global. So soon after weather forecasting adopted computer modeling, climate science did that too. The word, in fact, the phrase climate science is kind of a new phrase that came in around in the 60s or 70s after the advent of computer modeling and referred to, it was different from climatology, which had a kind of a geographical side and was often done by geographers as well as by meteorological scientists. So a climate model is essentially the same thing as a weather forecast model, but with one big difference, which is that instead of being run from an initial state that you measure, it's run for a long time and it generates its own climate because it has inputs of energy and outputs of energy from the Earth. And then you measure its statistical properties. So climate models have weather. There are hourly events, or events are on 15-minute or 10-minute time steps in a lot of climate models. So weather is happening, but you don't care about what the actual weather is. You care about what the statistical averages are over long periods, because it's not deterministic and you're never going to get a 50-year forecast of weather day by day. So, how is this done? So I want to talk a little bit about work process, and that's going to get us to this knowledge infrastructure business again in a few minutes. So in the early days of climate modeling, these models were built by very small groups, one person, two people, a team of 4 or 5. It was a craft, and there were 3 or 4 modeling centers that really where this began and continued. There was one at Lawrence Livermore Lab where the model was built but did not go forward. And essentially, there was no background against which to figure out whether they were doing this right. So this is I call this the lab phase because, of course, communication systems were also different then, and there was much more transmission by letter and by travel before electronic mail. It was slower. There was less possibility of working in large collectives that spanned large distances. There's a later phase in the 70s when this begins to be kind of institutionalized, and you get the really big labs, NCAR, the Geophysical Fluid Dynamics Laboratory, the Goddard Institute for Space Studies, not quite as big. You get them much more organized and really focused on the modeling project as the central aspect of what they do. So there's also data analysis going on in these labs, but I'm going to leave that out of the picture for now. And then you begin to get divisions of labor, of course, and as more and more processes are incorporated into the model, those divisions become really profound. So if you are working on modeling radiation for a climate model, you'll be in one group. And if you're working on a dynamical core that moves things around, you'll be in a different group entirely. You may never really know much about what the other group is doing. Resolution increased. There is no similar graph to this in AR5, so I'm using the one from AR4 that shows the first assessment report. This is actually Europe, which you can see very clearly here, but up here, this is like Linda's slide from yesterday that shows how different things look when you get higher resolution. Up here, you really can't tell that that's the North Atlantic and Europe, but by the time you get to AR4, with a resolution of about 110 kilometers in the grids, it's recognizable for what it is. Lots of physical process change too. Again, this is an older graph, but there's no similar one from AR5. It's still quite good. The early climate models didn't have a lot in them. It was mostly radiation, some precipitation, and carbon dioxide, and a few other things. And then they incorporate more and more processes: the land surface, friction, swamp oceans, ocean circulation. So then you get a whole other community, the oceanographers, working on modeling ocean circulation, which is like atmospheric circulation and just as important in the climate system, if not more so. And lots of other processes. Aerosols, thought to be extremely important now. And so on. So, this lab phase goes on for a while and still is really the core of a lot of work. But there is also, since the 1980s, a kind of even larger division of labor, which is now across institutions that are widely separated. So the CESM, the Community Earth System model, has 20 institutions or so are all part of it. Leaders of the different elements of that group are at different institutions. They have a giant meeting every year. There's a governance structure. It's really quite complicated. And since these models are now enormous pieces of software, up to 1 million lines or so of code, it's really not possible for any one person to understand what's going on in all pieces of the model. Oh, and I should point out that this slide and my next one are due to Steve Easterbrook, who's sitting up there and really ought to be up here. So this is a graphic that Steve and his student did of some of the major climate models and their code paths. It's not the what's going on here is the big bubbles are the atmosphere, the smaller bubbles are other pieces of the climate model. There's land surface, there's oceans, there are other things. And you see that they, how they're divided up and that they have to exchange data from one piece of the model, the atmosphere model, to the ocean and to all the other pieces on a time step. That's created yet another level of infrastructure around coding, which is the trade-offs, the handoffs from one piece of the model to the others. So there are now these very sophisticated modeling frameworks that will do this for you. They will regrid, they will allow you to some extent to take a piece of one model and use it with a piece of another model, and kind of mix and match. That was at least a dream of that idea. And it just keeps on growing. So we get models that try to do even more and incorporate not only the physical processes, but also sort of social systems involving our energy infrastructures, the other pieces of science like ecosystems, hydrology, and so on. In general, these kinds of models, integrated assessment models, just use the outputs from GCMs rather than trying to build on top of that structure. But they are, what they indicate is that we have more and more communities all trying to work together through modeling. So that whether or not you believe the results of any of these models, the point is that the knowledge infrastructure here is built on modeling. And one of the places that's very striking is ecology. So in the, block the slide list. In the 70s, the median size of the plots studied by ecologists was 1 square meter. So they would carve out a little piece and look at it very carefully and find out about it. There were also larger studies, lots of them. But after the climate change issue became important, ecologists began looking at much larger scales because there was money there for research and because it was interesting, and now they had something to interact with, climate models that were on these much bigger grids. And if you have a giant grid cell and you have nothing to say about what's happening across most of it, you can't interact. So there's been a lot of change in many sciences, all kind of orienting each other around modeling projects. Now, Steve Easterbrook has done some really interesting work, sort of ethnographic work at some of the climate labs, in particular the Hadley Center, where he found that, and this is true of other climate labs as well, though not of all of them, that the culture of lab production is still very similar to what it was in the 70s. The computer languages are the same, the kind of craft, one-off culture. We're building this model, and we aren't going to look at other practices. We're not going to incorporate techniques from software engineering and other disciplines. We've got our way of doing it, and we're just going to keep on doing that. That's been often been true, and there's a good reason for it, which is these are very big models into which a lot of work has gone, and they want to preserve what was done in the past. I don't know if this is still true. When I was interviewing climate scientists in the 1990s, many people told me that they had the experience of finding pieces of code that were written in the 1960s that were still there in the current model. If it's not broken, why fix it? So just leave it there. So of course there are lots of other pieces of the climate knowledge infrastructure. There's data, which I haven't talked about. There are journals and all the rest of the apparatus of scientific publishing, and lots of institutions that make this up. So, some of the challenges that climate science faces now involve updating software practices, figuring out how to handle these very large divisions of labor that mean that there's no, that there can't be a king. There's nobody who really understands the whole project and kind of has a handle on every single piece of it. So, how do you validate and verify as you're working there's also a big piece around organization and governance, and one of my many pieces of pie is this NSF project called EarthCube, which is trying to re-engineer governance in the Earth system sciences very broadly, not just climate science, but lots of others. And basically throwing a lot of money at scientists saying, please figure out how to work together and how to make your code interoperable. And the scientists are all saying, but we don't know how to do that. And the NSF is saying, well, we don't know either, but we're going to make it your job to have that happen. All right, now to the piece I want to spend the most time on. So, in science more broadly, there's this phenomenon going on right now of really bizarre problems with publishing. There's a lot of ranking of people by journal rank and citation indexing, citation counts, the H index, the I index, G index, all the things that you may be familiar with. And part of what that's doing is creating these weird incentives for people to rush to publish, to carve things up into smaller and smaller units. There's this acronym, the LPU, the least publishable unit, that goes around a lot, which is how you get the largest number of publications and therefore get a higher citation count, and so on. So this happened last winter. Randy Sheckman said, we're going to stop publishing in Nature and Science because these incentives have gotten so distorted. In China, they're paying people to get articles into these journals. And when you do that, you corrupt the process because you start to introduce, an incentive to skip steps, to fail to verify. And there has been an increasing incidence of fraud, or at least of people catching fraud in some sciences. Not really climate science, but others. And then there's this problem where when industrial labs go to reproduce the results that are published by academic scientists, they often can't do it. So in this Bayer study, they tried to, this is medical stuff, they tried to replicate 67 studies, and they only succeeded in doing it completely with 21% of them. So this large body, almost 65%, they couldn't replicate at all. Now, for somebody from science studies, that's not really that surprising, because you find that that reproduction, it's rarely possible to reproduce anything from the articles that are published. They don't give enough information. And that phenomenon has led to this kind of explosion of conferences on reproducible science and attempts to publish data and code so that reproducibility can be easier. So the challenge is publish everything. Your data and your code. This has been widely adopted in climate science. You will find most data sets online. You will find a lot of code from major models online. But publishing is still not enough. This would also be a very familiar result to someone from science studies. Because if you just publish the data or just publish the code and don't have really good metadata that explains what the code means and how it works, what the data are and where they came from, it's very difficult to know if you've done it right. It's very difficult to use it to reproduce things. So Steve and I and a couple other people did a special issue of IEEE software a couple of years ago where we asked this question, maybe open source will be the answer. And this, part of the reason for the reproducible science rush is that there's this we have entities like Firefox and Mozilla and Apache and so on that do this amazing open source production. Everything is out there. They get lots of kind of volunteer effort on building code, and that model has become kind of a idée fixe for a lot of scientists, that they should do that too, and then maybe somehow volunteers will show up and help them or something. It's not really clear what. But so lots of model codes are out there. There are lots of more specific models and tools. and there are now lots of data. So I taught a class with a climate scientist last winter on climate change informatics, and our first assignment was for them to go to the Earth system grid and download a data set. That was it. So they had a week to do this. We had 23 students, 6 of them were atmospheric scientists, 4 of those succeeded in downloading the data, and none of the other students succeeded, including the informatics students. So that says a lot about the interface to the Earth system grid, but it sort of points to this big problem with the whole paradigm of open source, that it's not just the kind of raw exposure of this material, but the ability of people to actually get it and use it. So here's climate.data.gov. This is a new, announced to great fanfare in April last year. It provides a kind of uniform interface to a lot of data sets, and it looks very neat. You can see what formats you can get the data in. There are many other, so this is the selection on climate. There are 400 data sets, and some of these have many data. In fact, they're not really data sets, they're data portals, and they have many more data sets associated with them. But the minute you start clicking on these links, you find out that it just takes you to the portal, and some of the portals are really good and some of them are really awful, and they don't really help you except that it organizes it all in one place. So the problem with this paradigm is metadata, and the problem with that is figuring out who's going to do it. Bench scientists don't want to do it because by the time they're done, they've collected and used the data, they're done with it, and they don't want to go back and document it for somebody else. So what we see in my research group is that often they push it down onto graduate students who are floating through the lab and may get partway through the process and then hand it off to another graduate student until it's eventually just forgotten or left unfinished. I've heard a number of high-level, sort of National Academy-type talks about this, and they're very interesting because they're always given by older people, in their 50s and 60s, and they say, well, we're not sure how to deal with this metadata problem, but the young people will know how. And then there's this other, much bigger question of whether it's actually worth it to do that. Because it takes a lot of time, and it requires a very meticulous approach that is hard to get. So, another community. This is machine learning. So these are people who do nothing but work with easily available online data sets and code. So these are the people for whom this should be simple. Victoria Stoughton did a survey of these people, and they said, basically, there's another slide here where they say, no, only about 60% of us are willing to share our data in our code. And why? Well, if we do that, we've got to document it, and then we're going to have to deal with people's questions about it. And their questions, some of them are going to be stupid, because they're people from other worlds that don't already know everything we know, and it's going to be irritating for us to handle that. So back to climate science. Let's look at CMIP 5. So this is the coupled monomer comparison project, the 5th round of it. Very, very important thing. This feeds into the IPCC reports. It's, they compare the results from all the major climate models on various standard experiments that are done with models, standard runs. So 27 modeling centers, 59 models, 96 experiments. Not everybody has to do every experiment, but it's almost 2 terabytes of data in this data set output. It's a big and very difficult project to begin with. But then, to make it really work, the idea was we'll now expose all the CMIP 5 data, and anyone who wants to work with this stuff can get it. But to do that, we need metadata. So this is these slides are from Brian Lawrence at the British Atmospheric Data Center, who was one of the central organizers of this process, and lost a lot of hair in the process. They designed designed a very sophisticated, complicated metadata questionnaire. Now, the metadata have to be produced not just for each model, but for each model run. So for every experiment, there's a set of metadata that have to be entered. The time estimate for how long this takes is between 1 and 3 months for one person to fill this in completely. And what they found when they looked at the metadata that were submitted was that, of course, they were incomplete, but also that there was a lot of evidence of cutting and pasting, because often often the answer to question, number 100 is the same as the answer to question 50. So you're going to do that a lot. Sometimes it's legitimate, but often what they found was that there are these really long forms with a lot of detail, and so people just bang through it without really reading every question. So a lot of the metadata isn't that good.
As the person that did that for GIS, I can tell you the questions were totally ambiguous 90% of the time as well. So like exactly what it was you were supposed to do in a way that was meant that was useful for anybody else was completely unsure, and there was no help whatsoever.
Yeah.
So
there's that side too. Well, one of the first, I did a little research project on governance, and one of the first telecons I went to was one where they were doing a very similar Earth System Curator project, which also involves a lot of metadata about models. And they were designing a questionnaire very much like this, and they had got a little setup. There were 25 people or so on this telecon. Most of them were climate scientists who had been part of this project for a while and were really knew what they were doing. They were all talking about the same thing. And the first thing that happened was they began to debate the meaning of the terms. So, Gavin's question is like, it's ambiguous. Exactly which version of this variable are we talking about here? So, this is becoming a really serious issue because a lot of institutions are now requiring the publication of both data and code. So especially in the medical world, in the National Institutes of Health, but also in the NSF, in NSF, there's a requirement now to have a data management plan as part of any proposal. This is 2 pages of your grant proposal, how you're going to expose your data and keep it available for others for some period. It is not funded, that piece of it. But you are required to do it and to expose your data after you can have an embargo period, but you can't keep it forever. So we talked about open source models already, and then there's all this kind of open access data. All right, let's look at a couple of controversies to illustrate some of the things we're talking about here. So the famous hockey stick controversy. This is Man Bradley Hughes, 1999. How many people are unfamiliar with this? Okay, a few. I'm not going to say a lot about it then, but basically, so up here on the right in red, you have thermometer records. So these are direct measurements. All the rest of the measurements here are proxies, so they're measurements that are derived from ice cores, tree rings, pollen, other things like that. This is the main path. These gray lines are error bars, so very large errors, of course, when you're back into proxy records, but the graph seems to show a very stark increase in temperature in the last half of the 20th century versus the global average. This graph became a target of something that was new in the early 2000s, which was bloggers. And in particular, this guy, Steve McIntyre, who runs a blog called Climate Audit. So this is where it gets interesting, because McIntyre's idea is that if you're a corporation and you have to give annual reports to your shareholders, you have to get an audit. And you can't get the audit from auditors who work for you, because that would be corrupt. They would have an incentive to fudge things, right? So you have to get an outside auditor, an independent auditor, to look at your books. So his idea is climate science is so important that it needs to be audited by people who are not climate scientists, because they have an incentive to feed their friends. So this, when it became became an enormous controversy. There's McIntyre and Mann. McIntyre requested some of Mann's data. Mann put it up on an FTP site and left him to fend for himself. McIntyre kept persisting and then started to ask for his source code as well as his data. Mann would not give him the source code. It went to the US House. It became the focus of many investigations by scientific bodies, the NSF, the NRC, AAAS, National Academy of Sciences. They asked for everything Mann had ever done, all his funding sources, all his data, all his code. You know, a terrible mess for him, and really kind of bizarre politically, but I'm not going to go into that part. So, now remember, this is the early 2000s. So that world I described for you at the beginning, where you own your data and your code, was still kind of in transition. It's only, you know, a dozen years later, but the transition is quite stark because, so Michael published a book about this last year, and he wrote up his experience in this controversy. And so he said, you know, why did I refuse to give McIntyre my source code? So, well, you know, first of all, I didn't actually need it because the code is just a computer representation of the algorithm. The algorithm was published. He could have found that and done it himself. Our code was our property. This is our work product. This is what I do. It's what, you know, it's how I can claim credibility. So I'm not going to give it away. We had done everything that the NSF required, and then it was source code today, but where would it end? Even email correspondence, and of course, in the ClimateGate episode, that's exactly what happened. Now, one way to read this kind of thing is that stuff like email is actually a form of metadata. Now, leaving aside the sort of horrible, politically motivated, you know, ad hominem attack mode of the ClimateGate types, you can understand why this is true. You know, people discuss their data and what they're doing to it on email. So one way they decide how to handle data or code is by trading these messages. So the messages are actually part of, you know, if you had a really elaborate idea of metadata, they would be part of it. Okay, so just to finish out the controversy, I've got one more small short thing. Okay. This was reviewed by many entities, and basically the finding was that there are now several other independent investigations of the same thing. They reached somewhat different results, but the basic trend is the same. And while there were some minor errors in the analysis, that they were not ultimately important. But this has led to a lot of other audits. And we have people doing audits of code. So these are actually two graphs superimposed on each other. You can't tell the difference because the differences are very, very small. The second graph was produced by a guy who took the GISTemp data analysis model, recoded it in Python, and then ran it again on the data to see whether there were some, and he found a few code problems. Would this affect the data? Answer, no. There are, you know, so here are a couple of the sort of official data sets versus the same data recalculated by individuals. Another, you know, land-ocean surface temperature anomaly, also recalculated by individuals. And then, a couple of years ago, the mother of all audits, this Berkeley Earth Surface Temperature Project. Fascinating because it was run by a physicist, Richard Muller, who was a climate skeptic, and was widely viewed as the savior of the skeptics by, for example, the Koch Foundation, who partly funded his project. So his idea was, you know, again, I'm a physicist, I'm not a climate scientist, so I'm going to audit the work of the climate scientists. We'll collect all the temperature readings we can find from everything, we'll recalculate it with our own methods, and we'll see what happens. So some of the skeptics said, well, okay, so whatever Muller finds, we'll save that. Well, what Muller found was, he just called up to Congress before this project was even finished, and you know, the skeptics are all chomping at the bit saying, yes, now we're going to get the real story. Mark got up there and said, well, so we've done our preliminary calculations, and guess what? They look pretty much like all the other calculations. So this is the Berkeley project versus the other data sets. They go back further in time. They have a lot more stations. They have almost 40,000 stations. Most of them are more recent, but they have older data as well. So they published this stuff, and they didn't wait for peer review, and this is part of the kind of knowledge infrastructure change I'm talking about too. Why did they not wait for peer review? So here's what they say. This is a very public project. Lots of people know about what we're doing, and they want to find out what the answer is. And if we don't tell them and interpret the results for people, journalists will find out about it, and then they'll do it. And you can see that this is something that happens a lot. So we're going to go ahead and put this out there as a kind of public preprint. And it was then peer reviewed in 2012, and again, it looks very much like all the other graphs. In fact, even so that Berkeley's the black line, you can see here the others converges very closely in the 20th century, but back here is actually lower than so you can see more temperature change in the Berkeley picture. Okay, so winding up. We have this challenge. People, and this kind of theory is becoming very widespread, that scientists are just one interest group among others. They have corruption incentives to review each other's work favorably and get it published. We now have the ability, and in some cases the capability, that is, people are actually moving into production, to put things out for review before they are published and open them for comment from anyone. I know of a few journals in France that do this routinely now, so there's like a 6-week comment period where anyone can comment before the thing is published. There's an irony here. A lot of this was aimed at the idea that somehow the IPCC is a conspiracy, and in fact it's the most transparent peer review process in history. But part of what's going on is that journals are the traditional organ of scientific publication, the choke point, the place where quality control is done. Their power is being massively reduced. We have this phenomenon of fake journals, which really exist just to suck money from people and then disappear. We have gray journals that are sort of not real journals. You get emails about this all the time. Please publish in our new journal. I can go into that more if you want in a minute. So here's the setup. So the traditional paradigm is this. I talked about this already. I want to finish quickly, so I won't say it again. But now data and model codes can be easily obtained. There are commodity tools for data analysis. The McIntyre-Mann controversy happened partly because McIntyre is pretty good at using kind of standard statistical packages to interpret data. It's not hard anymore. It's not a specialized skill. The one thing that has not changed is that understanding what data or models mean still requires expertise, and there's only one way to get that, which is through a lot of training. But in the world we inhabit now, authority and trust are being decoupled from expertise because of all these phenomena I talked about. So, I think I'll leave that slide on the screen in a minute, but this phenomenon is not going away. These movements are succeeding and pretty much have established themselves as the new paradigms for how science should be done. This means that, like other fields, climate knowledge is going to be engaged by more publics, different publics, sometimes may be improved by inputs from non-experts. I can talk about a case where that happened. But it's also making it easier to contest because not only the end products, like the journal articles, the synthesis, but also the whole process is much more visible than it ever was. And that means that contests are going to be harder and harder to resolve. Okay. So I'll stop here.
I think we have about
So the problem is we've got masses and masses and masses of complex code and complex data, and it's really hard to work out how to interpret that. So there's not really metadata, and partly due to this, we've seen this kind of change to these traditional structures, which are supposed to sort of support good epistemic practice or something like this. And so the answer to that is to make it all available. Why would that solve those two problems?
Well, I agree with you. It doesn't, and it's part of it.
So I'm just trying to, yeah, so my question is something like, how does that even get off the ground?
Well, it's an ideology. So it's important to understand that the word transparency is everywhere. Edward Snowden, that kind of situation. People believe that things are being withheld from them that they should be able to see, and code is part of that. So, there was resistance, like the piece I just showed you about the man, but he's not the only person who did that. I mean, Ben Sanders, another one who kind of resisted this for a very long time, and just wanted to say, well, no, you can't have code. But eventually just had to concede because they were going to get sued. And they were getting sued. In fact, the whole ClimateGate thing is based on some legal action to expose, in Britain, requiring the CRU to expose its data and its processes.
Right. So going on from that, I mean, it's not as if these two paradigms are really sort of distinct, and it looks like they're not mutually exclusive to me. So the sort of thing that you immediately think, given, so for instance, my reaction after the sort of Mama project, or whatever it was called, was something like, okay, good, we've just got some pretty good evidence. It looks like these guys aren't a big conspiracy theory. They're still using these traditional ways of producing good knowledge, and it's good that we've gone and got some independent people to check that out. But we don't have to do that all the time, just now and then. It looks like the two things aren't really in conflict. It looks like they can kind of reinforce one another in a way as well.
I think that will depend on your social world. So that's my reaction. I think probably most of the people in this room have that reaction when they see, but that is not the reaction of many people. And I was just telling Gavin earlier that I had some very sophisticated students in a seminar in France. These were master's students. They had not been really studying science or climate science before. They were supposed to give a report on some events in the 1970s, and they opened up with a discussion of this HARP project, which is this kind of studies of the ionosphere by bouncing a microwave beam off it. And it's quite powerful. It's about the energy of a single lightning bolt. But they thought that this was a government. They had read some stuff that made them believe this was a government effort to change the atmosphere. It was physically impossible that could be true, but they didn't know that. And the point is that this is a much larger set of social worlds are being exposed to these things now, and because of the kind of echo chamber phenomenon of the web, ideas about the problems with a science like this will not just go away when a study like that is done and confirms the results.
Yeah, and it's Emily, and then over here.
So to some extent, I don't think this is really a big problem. And in another way, it's a huge problem. There's an issue of incentivizing paying for it. So so just to get away from common sense for a second, I did studies with the NIH where they were interested in epilepsy prediction and detection. And there actually was money provided. So I was sort of reviewing different methods. There was money provided for some reasonable level of documentation, but I imagine most of that money went for paid charges. And the things that we do in the UK, we don't get any money for this, but now we're required to do it. So the thing is that the science this way costs more.
Yes.
And if that cost isn't being met, then there's a problem. The second challenge is that there's no reason to provide original source code for the kind of analysis like Michael Mann's. As you say, if the algorithm reproduces the results, the source code isn't needed. If the algorithm doesn't reproduce the results, there's certainly something to be discussed. But this code is so simple. Another implementation can be developed in public and leads to the same results. The only aid is for some ad hominem attack, or that code really doesn't matter if the results are the same. And And then this question of the wider pool of reviewers. So I'm a little afraid of a wider pool of reviewers because we have difficulty even with climate scientists reviewing our work. The issue isn't, again, I would welcome a wider pool of reviewers, but it means more work for the editors. The editor actually has to read and say, no, it's not fair to say these models were never intended to do decadal predictions, when in fact they're whole sections really easily discarded reviewer comments. So my question really is, so is there hope? I mean, if society wants to have this more complete version, then I think society can have that, but it can't have it for this, what I was saying before. I have plenty of students who are not going to be excellent dynamical systems people who could get a lot of reward out of filling that niche of adding metadata and trying to really be that intermediary. There are lots of people who could do this. I don't know any postdocs. I could never hire a postdoc to do that. So is there a way to overcome, if it was doable, is there actually a mechanism to incentivize people to fund doing it? Or is it just supposed to subtract from the time that's spent advancing the science?
Right. That's a great question. And I mean, I think practically speaking, I think the answer is that because this movement is succeeding, we will eventually figure out ways to incentivize and pay for it. But I hope that along the way, more attention goes into figuring out exactly what really needs to be published. Because, the fact that creating metadata is labor is very often just left out of this whole equation. It's just as if it's going to magically appear, and it doesn't. And some things are worth, cleaning up and publishing and for reuse, and a lot of things are not. So we need a better way of figuring out what is and what isn't. And the same debate will go on around all kinds of transparencies. Like there have been in a few states in this country efforts to make every public meeting open. That's a mistake because you actually need people to be able to go to a little room and make a decision now and then, instead of just always being confronted with a giant crowd of screaming demonstrators. It just doesn't work for public decision making to have everything always be open. But we need a lot more things to be open because we know that there are problems with our systems. So there's similar related problems, and I think the whole social system will eventually kind of move back toward a time of an ability to conceal things.
So we have a long queue of people waiting, so I'm going to try to work through it, but if you could make the question very brief, that would be really appreciated, just so as many people as possible can ask.
Yeah, so I'm a biologist, and I'm struck by the difference between this and what we see in genome projects, for example, where everything is open, the resources are open. If you're not providing your flights to people, then you get sort of struck off the register effectively. And it strikes me that the big difference is that with the genome project, people provide the metadata, they upload the data and things because it's useful. Whereas here, the only reason, and this is sort of getting to other questions as well, the only reason to upload it is because people are paranoid. And so that strikes me that that's part of the reason that people are not willing to invest the energy or the money in developing these metadata tools and things, is that for the most part we are trusting what each other are doing, and it's other people that are being paranoid about what's going on. Whereas, and I think if there is a use for those metadata and for those data sets that people are actually going to go back and make use of them, then there will be an impetus to do it. But in a genome context, it's absolutely useful, and that's the end product. And maybe that's the difference between sort of something being very successful and something that hasn't been.
I'll just say one sentence. So the CMET 5 project I talked about was a place where it was really important to get that metadata and get it right.
Yeah.
So it's not always useless and paranoid.
And did it work well?
Sorry?
Did it work well, I guess is the question.
It worked okay.
What is your take on private versus the institutional? So there's a lot of consulting companies that today they have a PhD or someone that has skills and training, and they're competing with a local organization or federal, whether it's NOAA, and they're giving data. So is that data legit, or it was never peer reviewed, like NOAA scientist? Or so could I use that data and still feel comfortable about it?
quite sure what you're talking about. Climate data?
Yeah, well, today there's companies that are producing data for money, basically, and they're outside all the government organizations. They're doing whether it's radar images, whether it's whatever data that they produce. Usually it's a PhD that didn't find its place in the system, and they're selling that information.
I don't know enough about that to give an intelligent response, so let's get Jared's question.
Oh, do I get to go first?
You know.
Age before beauty? Forget that. So I'm from, at the National Center of Atmospheric Research, and although not an actual climate modeler myself, I work with them a lot. And so I want to make two basic comments. One of them is, again, reflecting your comment over there about community standards in different disciplines. And for example, with the whole man debate, and of course that was discussed a great deal at NUR, we all knew Michael, the statisticians were very puzzled by this because again, statisticians, this community standard is to always provide your code. And I suspect they were like, well, why wouldn't you provide the code? And one of the differences, I think, goes back to the issue of that the climate modeling community developed without the support of formal software engineers. And the fact that the code is extremely ugly, very ugly. As a matter of fact, at one point, NSF came and reviewed the code for various models at NCAR and found them all to be deficient. Not that they didn't work, not that they didn't do what they said they did, but let's say again that they were very ugly. So quite frankly, I've always suspected that a lot of this just has to do with the embarrassment of having really ugly code. But that's non-trivial. I mean, I've written code. I'm not sure I want to have that out to the world and say, oh my God, it's written in F77. This is pathetic. No, but I think that's, I'm making jokes, but I think that's a real factor.
So your conclusion yesterday was yikes, and your conclusion today is yuck.
Pretty good, yeah. And that yuck can lead to yikes.
Okay, so I'll let Gavin have the last question, and I'm sorry for everyone who's still waiting, but this is going to have to be the last one.
So, one point, right? What is science all about? Science is all about taking a huge, massive data, synthesizing it, and telling you just exactly what you need to know, as opposed to just dumping all of the original data on file. It's a whole process of synthesis. If you suddenly insist that science has to be, no, it's not just synthesis, it's everything else as well, then, the whole point of doing science seems to be a little bit dubious. But,
It's a little.
yeah, that's fair enough. And I had another point about